Have you ever stopped to think about the programming tools you use every single day? They feel so simple, so convenient, almost like they're magic. But underneath all that simple convenience is this hidden world of really complex decisions and clever trade-offs, all designed to make our lives easier, well, most of the time.
I mean, we've all been there, right? You hit post and there's that little half-second pause, or a game stutters for just a moment. The reason for that, a lot of the time, is buried deep, deep in the code. It comes down to the basic choices the developers made about how to store and manage data. Today, we're going to pull back that curtain on one of the most common tools in any Python programmer's kit.
All right, let's dive right in with an old friend, the Python list. It's probably one of the very first data structures you ever learned about. You can toss anything in there, integers, strings, whatever. It's super flexible, it keeps everything in order, and it just works. But how it just works? Well, that's where our story really begins.
Yeah, because that simple, friendly little list is actually at the center of a really fascinating performance puzzle. See, depending on what you ask it to do, it can be blindingly fast or just painfully, shockingly slow. And understanding why that is, that's one of the keys to writing really great code.
And look, this isn't just some abstract academic question. This is a real-world problem. This question right here came straight from the r/learnpython community on Reddit. Someone wanted to know what the actual practical performance difference is between these common data structures. And the answer is that it wildly depends on what you're doing.
So let's look at the evidence. In one test, just accessing a single item in a list, like grabbing the second thing in the sequence, took about 22 nanoseconds. That is so fast it's almost meaningless. To put that in perspective for you, a beam of light only travels about 23 feet in that amount of time. It's basically instant. But now, get this. The same test on the same data structure, but this time doing a simple multiplication on every single item in a million-element list. The time? 64 times milliseconds. Now you might be thinking, hey, 64 milliseconds is still pretty fast. And you're not wrong. But here's the catch. A millisecond is 1,000,000 times longer than a nanosecond. We just saw an operation that was nearly 3 million times slower. And that right there is our big mystery. It's the same exact thing, right? The humble Python list. So how can it be a world-class sprinter in one race and a slow-moving giant in another? To find the answer, we have to pop the hood and look inside.
Yep, we need to go deeper, right into the CPython source code itself. That's the standard implementation of Python, and it's where the list keeps all its secrets.
Okay, so don't let the C code scare you. This is the blueprint. Underneath every single list you make in Python, there's this thing called a PyList object. We don't need to worry about most of it. Just zero in on two parts. Item, which is just a pointer to all your actual stuff, and this other little variable called allocated. And allocated, that is the secret ingredient to this whole thing.
And here it is. Here's the big reveal. The number of items you think are in your list, what you get when you call len, is not the same as the amount of space Python has actually set aside in memory. So even if your list has, say, 5 items in it, Python has already grabbed extra empty slots for more. It's always thinking ahead. This whole strategy has a name. It's called overallocation. And it is so clever. Because just think about it. If Python had to run to the operating system and ask for a little more memory every single time you added one item, it would be incredibly slow. So instead, it just grabs a bigger chunk of memory than it needs right away, leaving plenty of room to grow.
And this isn't random. There's a really smart pattern to how it grows. It doesn't just add one extra slot. It grows in these specific chunks. You can see the pattern here, adding a slightly bigger piece of memory each time it runs out of space. The whole thing is designed to perfectly balance using memory efficiently with making sure those expensive get more memory operations happen as rarely as possible.
This whole idea leads to a pretty powerful concept from computer science. Because those slow resize moments are pretty rare, the average time it takes to add an item to the end of a list is super, super fast. And it stays fast no matter how big the list gets. The fancy term for this is amortized O(1) complexity. But really, it's just a simple promise. On average, this is going to be fast. It's a beautiful piece of engineering.
So, okay, that explains why appending an item is so zippy. But that doesn't solve our whole mystery, does it? We found the secret to the list's speed, but what about the secret to its slowness? Why is an operation like insert, which is also just adding one item, so much more expensive? All right, let's walk through what happens when you try to insert an item somewhere in the middle. Imagine a crowded movie theater row. If you want to get to a seat in the middle, Everyone from that seat to the aisle has to stand up and shuffle over one spot. That's exactly what Python does. First, it might make some more room if needed. But then, and this is the killer part, it has to shift every single element after that point over by one. Only then can it finally drop your new item into the empty space.
So yeah, if your list has 1,000,000 items in it and you try to insert something right at the beginning, Python has to move 1,000,000 things. That's the hidden work. That's the massive cost. And that's why inserting is what we call an ON operation. The time it takes grows in a straight line with the size of the list. And just like that, mystery solved.
So, now that we've pulled apart the list and we understand the trade-offs that are baked right into its design, what do we do with this information? Well, it's all about choosing the right tool for the job.
This table really breaks it all down pretty clearly. A list is a champion when you're adding to the end, or you need to get an item by its specific position. But if you need to check if an item exists in the collection, it can be slow because it might have to look through everything. Now, a set or a dictionary, they use a completely different trick internally called a hash table. Think of it like a perfect book index. It tells them instantly where to find anything. That's how they get that blazing fast O1 performance for lookups and insertions.
So let's boil this all down into some simple, actionable rules. You want to use a list when the order of your items is critical and you're mostly just adding new things to the end. You want to use a set when all you care about is checking really quickly if something is in your collection and you don't care about order at all. And you want to use a dictionary whenever you need to link a key to a value, like a name to a phone number, for those instant lookups. You might be thinking this is all pretty deep in the technical weeds, but I promise you, understanding these fundamentals has a huge impact on the software that we all build and use every single day.
Knowing what's really happening under the hood is what changes you from someone who just uses tools to someone who really wields them effectively. It is the difference between accidentally writing slow code and intentionally engineering a fast, efficient solution because you understand the costs and benefits of every single choice you make.
So the next time you use an app, just think about it. Every smooth animation, every instant search result, it's all built on this foundation of invisible structures. The convenience we totally take for granted is the product of countless clever, hidden decisions, just like the ones that make a simple Python list work. It makes you wonder, what other secrets are hiding in plain sight in the code we use every day?